Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, welcome back for the final session of the day. So now we're going to turn a little bit. We're going to hear about quantum software and quantum safe cryptography from Mike Mosca. So welcome, Mike.
Oh, thanks very much, Krista, and thanks for the invitation to finally come visit Microsoft Research. So I want to talk about two interrelated topics that I've been focusing on more and more in recent years. As an undergraduate, I was interested, my background's in mathematics, mostly discrete mathematics, a bit of number theory, and I started focusing on public key cryptography and algorithms for public key cryptography. And that's how I got lured into quantum computing when my colleagues in England were telling me that physicists think they can break these problems easily. And after dismissing it a few times, and being forced to study it a bit more by my supervisor, then Dominic Welch, I realized this is actually pretty serious, pretty real and deep and interesting. So I started working in quantum algorithms, phase estimation, and many other things over the years. And in recent years, I started focusing more and more on these two topics that I'm going to talk about today. Cryptography is a very fun topic to work in. There's a lot of deep mathematics. You're solving puzzles, and it's also really important. So when you can have the marriage of something that's mathematically deep and interesting and really important, that makes it extra exciting. And of course, crypto underpins information security, the internet, and much more. Right? So for example, if RSA is broken, how can you connect your laptop to your computer to the internet? Or you have auto updates running all the time. You're downloading new software. Right. How do you know that's the authentic source? How do you know it hasn't been tampered with? And you'd really need to deploy a quick fix. And there's no quick fix ready right now. All the problems you hear about related to cybersecurity, well, I think virtually all, you hear about today in the newspapers actually don't have a lot to do with cryptography, which is a bit of a challenge for solving the problem I'm going to mention, because people in the know say, well, the problem wasn't a weak cipher. The problem was all these other things, okay, and more. Bad implementations. I made this list up well before all the publicized stuff in the last couple of years, even before the Beast attacks. I mean, we knew these were the potential weak links in the weak links, side channels and so on. I didn't, bad, broken crypto primitives, I didn't even put it on this list. It's not the main attacks today. Yeah, these are, bad trust assumptions. That includes people.
Specific people?
Yeah. Either in their intentions or their competence, right?
Well, also insider attacks.
Yeah. So, trusting the untrustworthy. So people often say you need more trust. Well, and then I saw this one lecture by this woman who said, actually, you need more trustworthiness, and you need more alignment of trust with the trustworthy. Right? That's where value gets added. The alignment between trust and trustworthiness, and just more trustworthiness. But just blind trust isn't actually necessarily a good thing. So the problem, of course, we all know about, and which has accelerated this field tremendously since the mid-90s, is Shor's algorithms, which compromises, surprisingly at the time, both of the widely deployed public key cryptography tools in one fell swoop. I guess we'd sort of hope that, well, if one is broken, surprisingly, we at least have the other one. But that's not going to happen with quantum computers. So we've had 20 years to do something about it. Okay. One of my cryptography friends was saying, you're trying to scare me with your quantum computer. I go to bed every night, afraid that somebody will find a classical algorithm for breaking these problems, right? And there haven't been major catastrophes. There have been weaknesses uncovered here and there, but no catastrophes. But another, a recent really nice advance. Some of my colleagues argue about how unexpected this is or isn't, but this was certainly a very impressive advance on the discrete logarithm in finite fields of low characteristic. Okay. Yeah. So which we may have used, but in the end, we aren't too dependent on such schemes, so it hasn't, not to mention there's a difference between a theoretical polytime attack and then actually implementing them. There's still ongoing work on studying the actual practical, for which instances do these attacks really make a difference. But we're not largely, the infrastructure is not largely dependent on this problem, fortunately. But it could happen tomorrow that there is and you don't need a polytime factoring algorithm, right? You just need one that's a little bit better than the one we have. And furthermore, people might not tell you that they have it. So there's already this nervousness out there. These are qualitatively different threats. There's the well-defined quantum threat, which we see moving on. And then there's there could always be this unexpected classical algorithmic advance. So with regards to the quantum threat, which is very well, we know the algorithm, we have getting a clearer and clearer picture of what the architectures might look like. But is it something we can just, thinking as a cryptographer now, can I put this off for another 20 years or another 10 years? Because the first order, we've procrastinated for 20 years. Not completely. Some very nice work has been done in the last 20 years, but it hasn't been at a very urgent pace, let's say. Can we keep waiting? Or do we need to really do something now? Well, that depends, okay? Because people will often say, well, you don't have a quantum computer. You haven't factored anything more than a really small number. It doesn't look like anything's happening. I'm going to just keep not worrying about it for now. But whether you should worry or not really depends on what you're in the business of. The information you're supposed to protect, how long are you supposed to protect it for? Let's say that's X years. A really important question is, how long will it take you to fix the tools you've deployed ubiquitously? Okay? How long will it take you to do that? That's Y years, let's say. And then the question we all get asked, surely, those of us working in quantum computing, how long before you'll have a quantum computer large enough to break these public key crypto systems? Let's call that Z years. I guess we should say Z years here. Okay. And then if X plus Y is bigger than Z or Z, then you should worry. You have a problem. Okay? You've already messed up. Because for the next Y years, you have to use the current tools because you haven't deployed the new ones that are quantum resistant, quantum safe. And you're supposed to be providing your customers X years of security, but you're not, because we'll break those codes in Z years. Okay. So this is the question you have to ask. And X is, depends on the business. Y I'll talk a little bit about, and Z is, we'll ask Rob what Z is. Really, we want a probability distribution on Z, because we don't know for certain, of course. But let me talk a little bit about Z, say. What can I say? We don't know is the correct answer, but the I don't know has changed a lot in the last 20 years. Okay, it's not I don't know and I have no idea. It's I don't know, but there's no reason to think it's going to be too long. I can't promise you it's going to be a long time. IBM wrote a nice perspective paper in 2011 where they said, it could happen. Rapid improvements in experimental quantum hardware suggest that a threshold for the design and the construction of fault-tolerant systems may be reached in the next 5 years. So I have another couple years to see if that prediction comes through. Then there's a really nice paper by Rob and Michele giving their outlook on superconducting, again on superconducting circuit implementations of quantum computers, where they track the right benchmarks. Well, certainly what the wrong benchmarks are, or how big of a number have you factored, because that's not the right, you're asking the wrong question. Okay, I'll get back to that in a second. But here are some of the relevant benchmarks, and they're tracking them. Things like qubit lifetimes. So this might look familiar. So I use this all the time now because it's the clearest thing in terms of communicating what's going on to cryptographers, right? Who are smart, but they're also very busy solving many important problems in cryptography. So there's these nice 7 stages to building a quantum computer. They all build on each other. Several implementations have achieved the first 3 or are now working on the 4th, which may be achieved in the next 2 to 5 years with significant probability, depending who you ask. But there's certainly optimism by serious people that this may happen in the short term. And then we'll move to the 5th stage, 6th stage, and 7th stage. It's not until you're in the 7th stage that you start factoring numbers and you start tracking how big of a number have you factored, right? That's the only place it becomes a relevant metric. There's other things we should be looking at in these lower stages. They're a bit harder to explain to people, but again, they're describing them in these papers, but that's what matters. And progress has been going, I think, very well. I mean, in the last 20 years, an amazing array of tools have been developed. We have people who are already thinking about all the classical control hardware, right? all these issues which 20 years ago we thought, well, that's the last of our worries. People are starting to worry about now, and doing very impressive work. Okay. So one of the other questions related to estimating how long it will take to break these systems, well, we have to. How many qubits? 100 isn't enough. Will it take 1 billion qubits and 1 trillion gates? Or 1 million and 100 million gates? I mean, these are important questions. This is years of scaling, right? Something else? Asymptotic complexity is obviously a really important tool in guiding the answer to these questions, but it gives just a very coarse-grained approximation. Okay. We need a more fine-grained study of the full tool chain between the high-level algorithms and the physical qubits. So what I'm loosely calling quantum software, right? Conventional software, and in the future it can be quantum software too, but until we have quantum computers, we can't use them to program themselves for controlling and optimizing the operations of our quantum bits. And this is an area where Microsoft's research, the Quark group, is playing a leading role. So I'm loosely using the term quantum compiler. I don't mean to offend anybody working in compilers, but I mean that the tools we'll need to take these high-level programs and map them down to the physical hardware. And there's been much foundational work has been done, started in many of these areas, but there's a lot more to do. We're starting to, certainly 10, 15 years ago, people thought, well, why is anybody bothering with that? But not everybody thought that, but it wasn't attracting a lot of attention, let's say. But as time moved on, I think it started to become clear to people that actually we should be looking at these questions. And experiments are already reaching a point where it's harder and harder to just have the grad students manually compile these things. It's already starting to make sense to have some sort of automated tools. Of course, it'd be interesting in the future, once we have quantum computers, we can use them to better compile themselves. This is related to David's comment earlier about one of the first applications of a quantum computer might be to design a better quantum computer. But certainly we can use a quantum computer to better program a quantum computer. So just to roughly sketch the tool chain from high-level algorithm, implicitly describes some circuits in terms of gates. Right? You have to compile them. Right? You have to make these gates. You're stuck with the fault-tolerant gates, right? So we have friends who are building things and trying to control them as best they can, getting effective physical qubits. And then our friends taking various approaches to fault tolerance to produce some small finite set of fault-tolerant gates. So the kind of tools I've done work in quantum algorithms, but in recent years I've been thinking more, our colleagues at Waterloo have been thinking more and more about how do you compile these circuits into these gates. So one of the first things we did was a exact multi-qubit gate synthesis algorithm based on a well-known method called meet in the middle. So we focused on, for the most part, on Clifford gates and the T gate. Right? We implemented them for up to 4 qubit operations. And the meet in the middle, it's very simple. Suppose the unitary U you want is synthesizable, has a decomposition of depth 8. Okay? So one brute force approach is just to try, construct every depth 8 circuit and see if any of them equals U. That requires complexity. It's x, some big constant to the power of 8. An almost quadratically better way to do this is to make a list, brute force all the depth 4 circuits, multiply them by U, and then here's a list of all the depth 4 circuits. See if you see a collision between these two lists. So sort the lists and just look for collisions. You can do that relatively fast. If you get a collision, then you have something times U is equal to W. So something depth 4 times the U you want to synthesize equals something depth 4. So you just take the inverse of this, and you've synthesized U. Okay. We weren't the first to apply meet in the middle. I think the first time I saw it in the literature was one of Igor's papers, I believe. But, and we applied many optimizations and smart data structures and so on to make this fast, because these it's still exponential. So you have to be smart if you want to get any reasonable instances solved. And one thing we did is we decomposed the Toffoli gate, trying to minimize T depth, and we're able to, if you just look at Nielsen and Chuang's textbook, there's a depth 5 circuit. We're able to compress it down to depth 3. We conjectured it was optimal because we didn't brute force every single Clifford. There was just too many for our tool at the time. But we were able to find a depth 3, and we conjectured it was optimal in terms of T depth. Because as many of you know, many of the state-of-the-art methods for fault tolerance, the way to construct T gates is much more expensive than the methods for constructing Cliffords. It's not always the case, but much of the main of the state-of-the-art literature has that assumption, has that property. Selinger looked at this and manually found a way to, if you really want low T depth and you're willing to buy ancillas, he was able to bring it down to depth 1. And the main idea is simply, so first of all, if you look at this Toffoli circuit, it's essentially just C0 and T gates sandwiched between some Hadamard. So if you can focus on just the middle part, it's just C0 and T gates. If you think of a circuit consisting of just C0 and T gates, the C0s don't do, all the C0s do is take, you have a string of bits, and it replaces one bit with an XOR of other, itself plus other bits. So a C0 circuit just takes a string of bits and maps it to, in a reversible way, a sequence of XORs of those same bits. There's some restrictions because you have to be able to go backwards. And all the T gates do, whenever you apply a T gate, it kicks a phase of e to the I pi over 4 times the value of the bit that you apply the T gate to. So it's either 0 or 1. So you're picking up a phase which is a power of e to the I pi over 4, and the power is just the sum, mod 8, of these bit values that were in the register when you apply the T gate. And the values in the register when you apply T gate is just an XOR of the initial bits. So Selinger's idea was simply, well, in depth 1, I can compute all the XORs I want. If you allow me as much ancilla space as I like, I compute all the XORs I need. I apply the T gates, and then I uncompute all that extra garbage I computed. Okay? So then what we did is said, well, let's suppose you have no ancilla or some other smaller number of ancilla. What you want to do is you have all these terms you want to compute. You try to pack them in. You try to do as many as you can at a time. Right? And then you minimize the depth that way. Okay. When we looked at what this was asking mathematically, so my master's supervisor at Oxford, Dominic Welsh, wrote, I think, one of the classic textbooks in matroid theory. So fortunately, I at least learned what a matroid was. So I remember telling Matt Amy, I think that's a matroid. So indeed it was. And this problem of trying to pack these things as low as possible turns out to be what's called a matroid partitioning problem. and Edmonds, who's actually at Waterloo, did this work, developed a polytime algorithm decades ago for solving this matroid partitioning problem in polytime. And so we run it. So, and then when you consider a general circuit, it's not just C0 and T's, there'll be Hadamards in between. So an obvious heuristic is, well, partition your circuit into everything in between the Hadamards. Okay. And then just optimize those chunks. And then also we try some heuristics which try to swap things before and after the Hadamards. Right? And we get some non-trivial reductions by this method. So that was one problem we came across. Well, two results there. Another nice example was related to 1-qubit synthesis. Again, in terms of Clifford and T gates. So a common tool you'll need is to construct a phase gate. And when you tell a physicist, well, we came up with a really efficient implementation of a pi over 10 gate, they first look at you like you're crazy. But then, at the physical layer, of course, a pi over 10 gate is easy. Well, usually. But you have to fault tolerantly approximate a pi over 10 gate in terms of your logical fault tolerant gates. So for example, a pi over 10 gate with precision, what was it, 10 to the minus 5 or so, Vadim? If you just use the state-of-the-art Solovay-Kitaev implementations, took on the order of tens of thousands, maybe over 100,000 gates, which is very frustrating to do a pi over 10 gate. Fault tolerant gates. So it's just, so it's a non-trivial problem. There are known ways to do it. Solovay-Kitaev. The problem is, in information theoretically, we believe there should be a log 1 over epsilon depth circuit, but Solovay-Kitaev gives you almost a 4th power of log 1 over epsilon. There's other methods, but they require an ancilla, say, or have more than linear depth. Again, some deep mathematics prove that these efficient circuits should exist, but now we have to find them. So the approach we took, and Chris and Alex actually developed some nice methods for optimally resynthesizing these circuits. Okay. So we were looking at synthesizing these circuits. And well, we didn't, where do you start? So we said, well, let's look at exact synthesis. Right. And if we could figure out something non-trivial about exact synthesis, then maybe we have a shot at finding a way to round off an arbitrary unitary into the unitaries that are exactly synthesizable, and then applying some exact synthesis algorithm. This was sort of the rough hope at the beginning. And it's clear to see that if you have Clifford and T gates, all of your unitaries are going to have coefficients in this ring. Right? Linear combinations of powers of the eighth root of unity times 1 over root 2 to the n. And it's clear that the only way to get the 1 over root 2s is with a Hadamard gate. So if you minimize, you find them, you can always make n large by multiplying top and bottom by root n. But pick the smallest possible n you can use to represent your matrix. That's a lower bound on the number of Hadamard gates. So it was a bit of a clue that guided us. So we showed that, this is Vadim and Dmitry Maslov, we showed that this is if and only if, actually, any matrix with these elements in this ring are exactly synthesizable, which was nice. And then what was really surprising, at least for me, is that you can, just by looking at the structure of the numbers, you can just read off the optimal synthesis, almost, right? So, Vadim realized what you really want to look at is the square of the, so let's just look at the first column of these matrices you want to synthesize. So let's suppose somebody hands you ht to the power of n. They don't tell you that's what it is, but they give you this matrix. It's Hadamard times t to the power of n. You look at the first column, take the square of these values. Again, the only way to increase this denominator is through a Hadamard gate. Okay. After the initial part. Okay. And what we're able to show is, so you're given a matrix, you compute this smallest denominator exponent. As long as it's bigger than 4, there's always some power of t followed by h you can multiply it by to bring the denominator down by 1. So you can just deterministically reduce that denominator exponent by 1 every time at the cost of at most 1 t or t inverse gate. And then Clifford's and Hadamard's. Clifford's. Hadamard is Clifford. Okay. So that I'm going to gave us a deterministic algorithm for exactly synthesizing things h optimally. Again, in terms of with an optimal number of Hadamard gates, and we could also show that it's t optimal. Though Krista and Alex had already come up with an algorithm for resynthesizing things so they're t optimal. So then moving on to the approximation problem. So this is great. Once you have something that's synthesizable, we have a deterministic algorithm for synthesizing it. What about the round-off problem? Is this just a trivial thing, just round it off and move on with it? Well, it turns out it was a lot harder than that. So you can so suppose you want to implement the pi over 10 gate, some phase gate. You can certainly round off the diagonal elements to something in the ring. Now you're left with, the algorithm only works if you have an exact unitary. So now you need to find a value y, so the resulting matrix is unitary. And sometimes such a y exists and sometimes it doesn't, but it exists with significant probability. So if it doesn't exist, just try again with a slightly different round off x. But computing that y was not so easy. I mean, it wasn't clear in the beginning, but it turned out to be a nasty number theory problem. But we're able to make it, Vadim noticed we can make it a simple number theory problem by adding 2 ancilla bits initialized to 0. So I'll skip the details, but if you do that, if you just add 2 ancilla bits initialized to 0, you're going to bring them back to 0. Then the round-off problem, so you just round off the first entry very naively, and then you have to find 2 other entries so that you have norm 1. Well, that's equal to, so you calculate some value m, and you have to find a, b, c, d such that their squares equals m. This is, in mathematics, there's this famous Lagrange 4 squares theorem that says every integer is representable by a sum of 4 squares. And my colleague at Waterloo, Jeff Shallett, and Michael Rabin, the famous cryptographer, had an efficient algorithm from the 80s. Well, yeah, he's famous for many things, but cryptography is one of the themes of my talk. So, so this is really neat. Okay. Now, it turns out we're able to remove the 2 ancilla bits. We could do it in practice. Peter Selinger found some nice algebraic methods for in polytime optimally, or near optimally, sorry, synthesizing these gates. And using other number theory methods. We use solving norm equations. And in practice, we could achieve fidelities of 10 to the minus 15 or so. But Peter found some really nice polytime algorithms with reasonable assumptions. Or I think his latest work, he assumes you can factor. If you can factor efficiently, then you can synthesize these things. This is where having a quantum computer can be useful for.
He just doesn't call it that.
Yeah, yes. First he was solving special cases of norm equation, and didn't call it that.
Okay. Anyway, so we started off on this work trying to improve the synthesis and optimization of these circuits. We didn't know what to expect, whether this would just be a mundane programming task, or whether we would stumble upon some really interesting questions. And we have already, I certainly didn't anticipate needing matroid theory or algebraic number theory, 4 squares theorem, or norm equations, and so on. Another idea we had was, because we stumbled upon this question of wanting to, not stumbled upon, we were presented with the challenge of trying to minimize the t-depth for deep reasons related to fault tolerance. So the Cliffords, by definition, are the unitaries that permute the Paulis when you conjugate up to a minus sign, right? So, and it's the T-gates that will map a Pauli to something other than another Pauli. So, in fact, a sum of two Paulis. So maybe an interesting way to just look at a given unitary is in the channel representation, right? Where you look at what the unitary does to the Paulis. It maps the Paulis to a linear combination of Paulis, and just store these values in a matrix. This is the channel representation. And just look at this matrix and hope that it talks to you. It says something interesting to inspire an efficient decomposition. So one thing we're able to do is reprove the optimal, the deterministic 1-qubit synthesis work nicely. Right. It's the T-gates that sort of make this thing other than a signed permutation matrix. So for example, here the colors just, one of these colors is 1 over root 2, and the other is a half, and 1 over 2 root 2, and so on. Right. There's some sort of structure here. It gives us some hint. So first of all, if the Hamming weight is 5, then you know you need at least 3 T-gates, because each T-gate you apply can just double the Hamming weight of a row or column. So I'll just summarize some of the things we discovered in this by looking at it in this picture. Another thing, we came up with a very nice way to represent these Clifford and T-gates that modded out a ton of symmetries and took the relatively naive brute force methods were exponential in n squared m. We're able to make it exponential in nm. Okay. So suddenly, remember I said the Toffoli gate, we conjectured it had T depth 3. With this method, we're able to verify that indeed it has T depth 3, and also came up with optimal decompositions of the Fredkin gate. How much, do I have 10 minutes left, or how much?
7 minutes.
7 minutes, okay. So just to wrap up, I mean, our group, Microsoft, and a number of other colleagues around the world have been developing, this is just a few examples of some nice tools. I mean, we have Igor in the back who'd been working on this for many years. I mean, reversible computation, for example. These are all important primitives in optimizing these circuits. There's a number of groups around the world who've been developing tools over the years that'll help us when we reach this stage 4, stage 5, and the Deborah-Schulkopf hierarchy there, where we're going to be doing implementing logical circuits. Then you really need these tools. And these tools are important for determining when will we actually be able to take advantage of these, chemical simulation algorithms or these other, material design type questions, or factoring large numbers, So that's a very long-winded answer to the question of what is Z. I don't know, but there's reasons to, think this will happen in the medium term. And there's a lot of ongoing work to determine when exactly this will happen. How long will it take to, yes?
You had a question, how many gates for RSA 2048?
Yeah.
Do you have an answer for that yet? Or?
What's the best guess we have as to how many, I think it's at least, at least 10 million is probably the lowest guess I've heard. But I don't know of a coherent, end-to-end answer to that. It depends on a lot of things, from the architecture to which fault-tolerant code you're using and so on. But it's a lot. And I've not seen a sort of reliable end-to-end calculation lately. But even if you did, it would have so many assumptions that. So how long will it take us to retool the infrastructure? So this, it's not likely to happen in 5 years or in less than 10 years, depending. Even if there's a 5 or 10% chance of it happening, then we really should be ready for it because so much is at stake, right? But how long will it take us to fix the problem? So we have ideas for how to fix it. There's been a lot of research going on since the beginning of public key cryptography and alternative public key cryptography. In terms of deploying alternative classical ciphers, you need to make sure they're secure against quantum attacks. And there hasn't been, I would say, a ton of work in that direction. There's a little more lately, but that's something it'd be good if we could find ways to motivate bright young quantum algorithms experts to study these problems so we can gain some degree of confidence. And we need eventually to get the standards and practices ready. Just because there exists a code that would solve all our problems doesn't mean it's going to be there when you need it. Because it takes years of engineering, implementation engineering, side channel analysis, and so on, and standardize all the political and standardizing work necessary to actually get these things deployed. So it'll take, in fact, a new workforce, and that's one of the things helped develop at Waterloo is a training program for our students to learn all the different areas of cryptography and security and so on, as well as some of the non-technical skills, like learning about standards and certification, to take these tools that we're all working on and bring them to actual practice. Because I believe that now's the time to be planning this transition to a quantum-safe infrastructure. So one of the things we need to do is take these alternative schemes like lattice-based cryptography or code-based crypto and just look at them with quantum attacks, right? So it's one. Here we looked at what Grover's algorithm would do to the best known lattice, short vector and a lattice algorithms. And it'll help a little bit, right? So it means you have to increase your key a little bit. But we need to study these more intensely and try to do even more sophisticated things with our quantum algorithms. And they still need more classical scrutiny as well. So the solutions that we know of to replace RSA and the discrete log-based systems, there's two families. They work well together. One is what's often called post-quantum cryptography, a term coined by Dan Bernstein. They're classical codes. You don't need quantum technologies, which is very convenient. And they're computationally secure. So we're still in the realm of, well, we hope they're secure, but you have to do all this hard work to build confidence in the key lengths and so on. And then there's quantum cryptography, which we've heard about since the early 80s, QKD in particular. Quantum crypto, we didn't really hear about it. It existed in the 70s, but we didn't hear about it really till the 80s either. Right? They need some quantum technologies, but again, QKD doesn't need a quantum computer. It's already commercially available. And the nice thing is, especially for QKD, there's no computational assumptions. But they work well together. So for authentication, you can use the equivalent of today's signatures, which use the same kind of tools as public key encryption. So rely on what's in complexity theory called a trapdoor predicate. There's a stronger form of signature that, strictly speaking, you only need a one-way function. They historically haven't been as efficient, but people have made them more and more efficient and are implementing them. Of course, QKD, historically, we talked about symmetric key authentication, but there's no reason you can still use these other kinds. There's a variety of alternative public key cryptography, and quantum key establishment is another way to establish keys in a sort of public key setting, right? An important point when you're trying to compare the strengths and weaknesses of QKD, or the alternative to QKD, which is what we currently do today, and of course I think we're going to keep doing in the future with these new post-quantum ciphers, is equivalent to you establish a key through public key encryption. You don't actually encrypt with the key normally. You just use that key in a symmetric key cipher. From a complexity theoretic perspective, it's called a trapdoor predicate, whereas signatures only require a one-way function, strictly speaking. And there aren't too many, that's Charlie Brown's Christmas tree, there aren't too many alternatives for public key encryption that we sort of trust. And there's this extra mathematical structure that in general makes them extra vulnerable. Whereas there's a plethora of good one-way functions, hash functions, and symmetric key systems. Now QKD will allow you to establish key. You need authentication, which in principle you can do with one of these one-way function-based schemes if you want to do it in a public key setting. You don't need these potentially more vulnerable, though they're more efficient typically. That's why we like them, signature schemes. So there's various pros and cons to mixing and matching these different ways to authenticate, establish key, and then use the key. What we typically talk about in QKD is you use a Wegman-Carter, information theoretically secure authentication, QKD, and one-time pad. Every top to bottom, it's all information theoretically secure. That's certainly great. But on the more practical end of the spectrum, just going down, we can slowly makes stronger and stronger assumptions. So for example, you could use a more conventional signature scheme, QKD, and then AES, for example, to encrypt. To do that means you're trusting the short-term security of a trapdoor predicate and the long-term security of a one-way function. The classical alternative, which we'll need because we're not going to have quantum internet in the near and medium term, as far as what we know how to do today, trapdoor, some sort of signature scheme, and a trapdoor predicate-based key establishment, and then some symmetric cipher. The long-term security of this relies on the long-term security of a trapdoor predicate, which is a much stronger assumption. Right? So this is one of the advantages I like to articulate to using QKD. So just to wrap up, quantum mechanics forces us to reinvent the foundations of our cryptographic infrastructure. We don't have a choice. And it's important to emphasize to people that quantum safe is a necessary condition to be cyber safe. Okay. Often people are hesitant to adopt or consider adopting these quantum safe alternatives because they're not as efficient as RSA and so on. But you're comparing something that's quantum safe to something that isn't, right? These things will be broken at some point, so you have no choice but to pick one of these alternatives and maybe make them better. And we're very lucky that we have a head start. We have this warning. It's not like we built the quantum computer first and then realized they undermined information security, public key cryptography as we do it. We had this 20-year head start. We still have a few more years, but we shouldn't bet on it being too many more years. The planning, at least, I'm certainly not advocating stop using the current tools and quickly this mad rush to this new untested set of tools. They're not untested, but they haven't been tested as much as the stuff that we're currently using. But start planning, start making the smart steps in that direction. So to summarize, there's a lot of very interesting, there's sort of these two interrelated areas of research I've been interested in recent years. And I like them very much because they allow me to explore some very deep mathematical questions. And they also have practical implications in the short and medium term. So well, thanks a lot for your attention.
So Michele, I think you raise a very important issue. In some ways, I'm thinking about quantum mechanics or quantum computing as being the Y2K of cybersecurity. But there is this big issue of how much software is currently involved in cybersecurity and how many lines of code would have to be changed in order to make our global information infrastructure secure. Have you looked at any estimates of how much?
It scares me because just replacing DES with AES took like ages, right? And that's
well, the reason I asked
a trivial, well, from a mathematician, it's in relative scale an easy thing to do.
Most people don't realize how much software the world uses to run its affairs today, and the numbers are staggering. And if we look at the cost of changing software or writing software, it's enormous. I had guesstimated that maybe 1 trillion lines of software to 100 lines a line. So how much do we have to change, and how much is going to cost, and who's going to pay for it?
Well, that's what scares me about that Y parameter. It's not, it doesn't suffice for there to exist a solution. It has to actually be implemented, tested, battle tested, side channel tested, everything, and then standardized, and it's just years and years. And of course, we'd move faster if we had, as we see the quantum computer approaching, but it's just so many years of engineering. I don't know if Greg, if you have, you want to even try to guess that, an answer to that question, but it's enormous as far as.
Numbers,
okay.
Right.
I'll give you some numbers in terms of years that we've done for the past decade or so. It took us to move off of MD5. We started in 2005. By 2010, we were not done. And this does not include adoption by external parties, came even after that. Even today, we have certificate authorities still use MD5 for certain things. So a decade is a rough estimate to move to a new algorithm displacing an old one. It includes writing software, shipping your product, making it available, people purchasing it, people deploying it, and then finally using it. And test, all literally long lines.
You're making it sound hopeless.
And in 2006, we shipped built-to-curve cryptography. There's only one company using it today. That's Google. And we started using it fairly recently. So there are the numbers.
Let's take one more question from Burton
Yeah, all the-
Matthias. While Matthias sets up.
All the quantum key distribution stuff that I've heard about requires transport of quantum state between the communicating parties, which strikes me as being absolutely radical in terms of the infrastructure required. The first talk today was very interesting, though. It was about bootstrapping quantum-derived entropy to multiple sites. It may be that, I mean, it'd be interesting to sort of look at to what extent can we use the internet as much as possible. Use the triangle inequality, use all these tricks, and figure out a way that you know, companies that provide web services do the quantum transport, and the rest of the world can live on something simpler. And has anybody looked at this sort of a hierarchical approach to?
So QKD can, in principle, work on deployed optical networks.
I'm talking about, deployed optical networks to everybody's mobile phone? I don't think so.
I don't. So like when I gave that, I think we're going to need, the conventional post-quantum tools deployed ubiquitously, and that'll sort of be the backbone. But
Sure.
But QKD does offer some advantages for customers who are able and interested in having those advantages.
Yeah, what I'm wondering is there some way of using QKD to get close to where you're going, and then bootstrap from that, generate randomness, for example.
Oh, I see.
That
Yeah.
kind of thing, locally, or more locally, so that your mobile phone doesn't need to have a coherent optical link to something.
It's interesting.
I don't know, but I mean, it's a direction to work in. Say, let's not go after the QKD thing in pure form. Let's see if we can build a layer structure.
It's a good idea. Thanks.
Might work, might not.
Well, good to meet you.
Yeah.
The dash after this.
Yeah.
Yes.
Let's thank Mike one more time. Okay, so now we have our final speaker of the day. We have Matthias Troyer, and Matthias is going to speak to us about quantum high-performance computing, or high-performance quantum computing. I think this means he's going to talk about quantum algorithms for materials. So let's welcome Matthias.
Okay, thank you. And I changed the title a bit because Matt Hastings talked about the quantum chemistry three methods already. So I wanted to focus more on the high performance aspect of quantum computing, and I still don't know whether it should be called quantum HPC or HPQC, and I leave that to Burton to help us decide. But let me step back in time, and we've seen the Antikythera mechanism shown multiple times already. So we've come a long way first classical. I like the harmonic analyzer by Kelvin and so on. Those machines were analog, and just like the quantum machines that we have now that are analog, they're simpler, but they suffer from scaling problems, they suffer from calibration problems. The digital machines came later, they are harder to build, but now we have some amazing machines, and the question is, do we need anything beyond that? And so let me show you the scaling of the fastest machines in the world according to the top 500 list. and how it increased exponentially for more than 20 years. In red, the speed of the fastest machine. In yellow, the number 500 on the list. And in blue, the sum of the top 500. Some people are starting to say, hey, it starts to bend over. There seems to be an end now. The fact that the fastest machine has been the same for 3 lists in a row, that is for a year, doesn't matter much. That has happened a few times. So we're still on track, I think, to reach at least an exaflop. But the question is being asked, what do we do once this scaling Moore's law ends and it stops? What should we do then? My first answer is write better software and invent better the algorithms. But let's focus first on the hardware side. And we can go to quantum devices. And some we've seen already, like quantum random number generator. Of course, when you open it, it's not so clear how much there is quantum. We have quantum key distribution systems, but there are also quantum hackers that can break them. We have quantum simulators. We have the machine by D-Wave that I should not talk about. And in the future, we might have some quantum computer where the only thing I know is that it will run a version of Liquid, which will then probably be renamed into Windows Q. Now, last week I've been at a conference in Italy on high performance computing, where Paul Messina from Argonne organized a session about enabling technologies for beyond exascale computing. And the goal is, when he defines it, it means he doesn't mean something that's a yatterflop. He means something that finally changes totally fundamentally how we compute. And with that in mind, if that is the context in which these people view quantum technology, then we should not compare, is a D-Wave machine faster than my laptop or not? But we should compare it against the fastest special purpose machines that we might be able to build classically in 10 to 20 years. And that is beyond exascale. So that's kind of the reference. It's not about beating my laptop by a factor of 10 or 1,000. I don't care about this. This is much more. So let's look at those devices with that in mind. Quantum random number generators are nice. They don't compute, so let's drop them. Quantum encryption is a different problem. Let's drop with a D-Wave device. At the moment, it's roughly like my laptop, and it doesn't scale better, so that is clearly not a candidate. Building that machine better with better qubits might change the game. We don't know yet, but currently it's not. Let's look at quantum simulators, at the analog ones first. And they've been widely used in physics to solve some the quantum problems. And they've been chosen a few years back by science magazines to be one of the breakthroughs of the year. So what is the problem? The problem is that of basically quantum chemistry, material simulations. When we want to solve a material problem exactly, the problem is exponentially hard on classical hardware. However, Kohn and Sham invented density functional theory, where the basic idea is that if you want to know most of the properties of a material, like the ground state energy, the ground state electron density, and many more things, vibration, spectra, and so on, you don't need to know the wave functions, but you can actually calculate it just using the density. And the density is just a density in space. It lives in a 3-space dimension, while the wave function of the n particle problem lives in a 3n space dimension. That's what makes it exponential. Now, the problem is only one knows that one can do it that way, but there's a little problem that you need a certain functional of the density that gives you the ground state energy, and that isn't known exactly. So one has to approximate it, and that works amazingly well in practice. You can calculate the spectra of semiconductors like silicon. The band structure comes out nicely. Here's the Fermi surface, the band gap. It just works beautifully. For most simple metals, insulators, semiconductors, proteins, and so on, for most problems, we can calculate things well enough. And so Walter Kohn and John Pople got the Nobel Prize in chemistry in 1998 for that. So what's the problem? The problem then is that there exists some classes of materials where this breaks down. And you can, for example, look at the cuprate room temperature superconductor. They have been very interesting because the transition temperature of the best known superconductor remained low at about 20 Kelvin for decades. And there's been one law in finding a new superconductor that is never talk to a theorist. Now, in 1986, Bednorz and Müller had a theory that turned out to be wrong. Based on the theory, they looked at a material and found, hey, the superconducting transition temperature is much higher than before. It jumped up by quite a bit. And then soon after, it jumped to above near liquid temperatures, jumped up soon to about 140 Kelvin, so a factor of 2 below room temperature, and is stuck there since then. So we really want to find out, for example, why is it stuck, and can't we push it higher by a factor of 2 and we have room temperature superconductors? And this time there was a big hype how we'll have levitating trains and so on, and what we can have when we have it, but then they didn't find it in the lab. Now the question is, can we simulate it? And yes, one can. One can use the same density functional theory. And what you get when you simulate the undoped material is you find there's the band structure here, there's the Fermi level, and it cuts beautifully through the conduction band, which is half filled. This is a metal. According to all the calculation, it's a metal. When you actually build it, it's an insulator. So the problem is that density functional theory here is not even qualitatively right. And this is an insulator which, when you dope it, it becomes the superconductor. And we want to understand that. So we want to know what causes superconductivity here, and want to know whether we can design a room temperature superconductor or not. It might not be possible. It might be. If it's possible, then yes, we should try and do it. So what do we do now? Because we can't simulate it exactly. We simplify it. We make a model. We start from the superconductor. We look at the crystal structure in 3D. That one finds that the important features are some 2D planes here of copper oxide. One focuses just on those 2D planes of copper oxide. This is still too complex to solve exactly. And then you look closer, and you can focus just on that one single band that cuts the Fermi surface. So you focus on a single d orbital of the copper, and you make a model just for that. You make a simple effective model, and you try to solve this model. Now this model in its simplest form is called the Hubbard model. This is a model in 2D on the square lattice. You have the electrons spin up or down. You have two terms. You have one term T here that hops the electron, and the Coulomb repulsion, which gives rise to this into the 4 terms in quantum chemistry, you simplify it. You only take the local term of 2 electrons being in the same orbital. And that costs energy U locally. So it's kind of the simplest model that you can take. If you drop the hopping term, then it becomes trivial. If you drop the U term, then it becomes the free fermions. This is the simplest model you can have for strongly interacting electrons. And it's immediately obvious also why those materials are insulators. Although you can have up to 2 electrons per lattice site, if you have a strong repulsion U, you only want to have a single one. If you then put one on each side, it's just stuck insulating. Now we want to dope it a bit, and we want to solve it. And here's the simplest model. I have only 4 states per lattice site, but the problem is still exponentially hard to solve in 2D. And so far, we have some ideas of what the physics is, but basically nobody has really solved it yet. This is something that we might be able to do in the next 10 years to learn something about it, transition temperatures, maybe being pairing ring mechanisms, but we can't really solve it on classical hardware. And so the idea then was to follow Feynman's suggestion and use a quantum device to solve such a quantum problem that we can't solve yet on an exascale machine. They use about $2 million worth of equipment, mostly lasers, lenses, mirrors, work for 3 years, control noise to the nanokelvin levels, cool it down. So this is really the coldest place in the universe. It's a few nanokelvin. And then the atoms they place in there start behaving like the quantum objects, and they form a Hubbard model. So they take atoms which they cool down. They place those atoms in an optical lattice built from the laser waves, and the effective model that describes the physics of these very cold atoms is the Hubbard model. The atoms sit coupled to the laser light through their dipole moment. They want to sit at the maxima of the laser light. That's the potential minimum. The atoms can hop. When there are 2 atoms nearby, there's some repulsion. That's the U-term. So they basically take hardware and build a Hubbard model from quantum Legos. And then one has the Hubbard model realized. One can tune the hoppings by changing the laser amplitudes. And you can basically do 1D, 2D, 3D lattices, super lattices, and all just using lasers. And you can use bosons and fermions and so on. And the claim was now we can solve all models of condensed matter physics. We've solved condensed matter physics. Now there are 2 problems. First of all, you have to build it and then show that it works. Okay, so that's the first problem. But that one can actually test. So what we did is we asked them, what exactly have you built? And we asked them the question for bosons, because bosons we can simulate. And so using bosons, we asked them, what have you built? Which atoms, which trap, which laser, and so on. And then we just simulated for the bosonic version of the Hubbard model what they should see. And we measured the momentum distribution function. And what one sees is that at high temperatures, it's pretty broad. When you go to low temperatures, some spikes appear at the momentum that's multiple of the 2 pi here. And that is an indication of the onset of Bose-Einstein the condensation, where the bosons condense. And one sees clearly there's a sharp onset where it happens, and it looks the same in the experiment and in the simulation. Those simulations take for each plot 1 day on a PC on a single core. These simulations in the lab take for each image a few minutes, an hour in the lab. And the agreement is excellent once we really understood what they really build in the lab and how they calibrate things and so on. Now, these things work, but this is the problem that we knew how to solve. What about the fermionic Hubbard model? The good news is that they get into the regime where it's hard for us to simulate it when one looks at dynamics of the atoms. If one just looks at the finite temperature properties, the static ones, then one sees there are limitations because these are analog devices. One problem is calibration. Another problem is cooling. They want to cool these atoms down, and the problem is, how do you cool something that's at nanokelvin temperatures? You don't have a cryostat to cool them lower. So we have a problem with cryostats. So you need to remove entropy, and that's been hard. So the scales, what one has done is the Fermi energy is about up here. These gases come down to about 1/10 of the Fermi energy. These are pretty quantum. But compared to the temperature scale in the cuprates, this is 5,000 Kelvin. The first simple magnetism that we can still simulate sets in at 3 times lower temperatures. Superconductivity, one needs to go another factor of 10 below. It's a huge challenge reaching these points, and then if one manages to reach it and manages to simulate it, it's only for the Hubbard model, because using those atoms, these quantum Legos, I can build a Hubbard model, but not much more. So what we really want is we want to build a quantum computer. But that quantum computer should be useful. It will cost a lot of money, as we know. It will take decades to develop. So the question that comes up here, and that we've been discussing with people here at Quark and at Q, is what do we do with quantum computing? What do we do that's beyond exascale? So what are the important applications? Okay, that we know. That we can solve in a quantum computer, that gets harder. And that at the same time, we cannot solve it on the best special purpose post-exascale machine in 10 to 20 years. But this is the yardstick. And that's what we should think about. And I've asked that many people, and I got immediate answers. Shor's algorithm for factoring. I'm not sure this is a killer app, because once we can build such a machine, there will be in a post-quantum cryptest we just heard. Then there might be a few users who still want it, but I'm not interested anymore. Rover search is what one hears next. And it's often described as searching in a database. But this is not the application, as we know, because if I have a real-world phone book or database, I need to implement that query lookup, and that needs access to all the data. So I cannot do it faster than with order n gates, a single lookup. And with order n effort, I can solve it already classically. So it's only useful if you have an oracle that you can compute efficiently. And nobody so far has told me what is the real killer app that needs this. Then I want to go into more details on 3 methods now: on quantum PageRank, on linear systems, and on material simulations, to just show that in the literature there are many claims that one has to question and check carefully. Quantum PageRank, there was a paper by some people at the USC. They've shown how you can solve the PageRank problem in log n time. You get exponential speed up over a classical machine. But in order to do that, they don't encode the vector in log n qubits as one could, because then it's hard to write the code, but they use unary encoding using n qubits, and they just use the states where one qubit is 1 and the others are 0. And then they develop a nice diabatic method to solve the problem. And basically one has to evolve the system diabatically to find the ground state of a simple spin model that one can build. But if you look closer, the spin model has all-to-all couplings. So for n web page rank problem, you need to implement n qubits, and you have n squared couplings. And if you do all of those couplings in an analog device, for example, or digital ones in parallel, using n squared couplers, then one can solve it in polylog time. Let us compare that to classical hardware. If I don't go parallel, if I do it serially, then classically I solve it using the power method with the few iterations of the matrix vector multiplication. The matrix is sparse, so any time that this order n, I need hardware. Oh, okay, so and I want to. What did I show here? No, I just want to look at the general purpose. Yes, I need memory that is linear in the problem size. I need to store the vector. The quantum device has the same. The time is linear if I do one term after the other. It's actually quadratic. I should fix that because it's n squared terms. It's quadratic. So serial, it's worse. What about if I do it parallel? If I do it parallel, those people did check the literature and they didn't find any classical logarithmic time method. And we talked about it, and I said it should be possible to actually write down a parallel classical algorithm. If I use n nodes, for example, then I should do it faster. But I found out it depends on the bisection bandwidth of your network. And if you use the typical 3D the cost per network, then the bisection bandwidth limits it, and the scaling goes from n down to the cube root of n. You can go to log n, but in order to go to log n, you need an all-to-all network, which we wouldn't want to build. But with an all-to-all network, we could do it. It's better here because the matrix is sparse, so you don't need it. All-to-all, I just need it built like the connectivity of the web graph. But what the quantum algorithm proposes is to build such an all-to-all network in hardware, and then the time goes to log n. If we do the same on the classical machine, it's also log n. The hardware requirements are better for my classical special purpose hardware, although I think Burton would never want to build it. But I think neither would we build this. So you have to really compare, not just saying, okay, you have here an idea of how something can be done in log n time, but you have to compare that you compare to classically to something where the hardware requirements scale in the same way. If not, it's just not true. So the quantum speedup here vanishes when you compare to parallel quantum hardware, and it's not a quantum speedup, it's a parallel speedup. Yeah?
There's a lower bound for classical computation in 2 or 3 dimensions. So if you assume that the time to communicate from point A to point B goes at least linear with distance, then you get the n to the power 1 over 3 for 2D and n to the power 1 over 4 for 3D. And you cannot get log n. So to get log n, you need to assume instantaneous communication.
How about quantum?
I have not seen it, but I suspect that it also holds for quantum.
It should be the same, yeah. Okay, so don't get fooled by the parallel speedup. Now, solving linear systems of equations. Is that a killer app? I'm not sure, but at least it can be solved in log n times, but we have to be careful. It requires that I only need to know log n bits of the answer. That can be done. The problem has to be well conditioned. And in order to apply this algorithm, we have to evolve the right-hand side with the exponential of the matrix, which can be assumed to be the mission here. So for a general time evolution, if the matrix has n squared entries that are different, I cannot do it with less than n squared gates because I need to get at least each of those data points in. The complexity can't be better than that. And classically, if I can use an iterative solver, I do matrix vector multiplications, they are n squared. It looks like the same scaling. Now, the group of Seth Lloyd proposed a quantum algorithm to do the time evolution with a general matrix in log n time. But this needs something called the QRAM, a quantum version of the RAM that you access here with the superposition of the memory addresses. And into that QRAM, you have to load a square root of the matrix. Now, I need n squared gates and qubits to implement it. And to calculate the square root of a matrix, I have to do that before I use it. Classically, that needs n cubed. In n cubed time, I can solve any linear problem. Now, let's assume I don't get the matrix, but I get the square root. Does this help? So then it could beat Gaussian elimination, but if you give me n squared hardware, I can just make a special purpose device where the memory not only stores the matrix, but it does a matrix vector multiplication, and I can do the matrix vector multiplication in memory in log n time. So then I get to a scaling that is very similar. It now depends on which algorithm converges in fewer iterations. But if I have to store the matrix, again, there's no speed up. And that means that for many linear problems that depend on data, this might not be a good approach either. One can solve it efficiently if you can implement that evolution by short circuit that was shown in a nice paper by Kleider et al. That was already shown by Dave Wecker yesterday. They look at the wave scattering problem. And here, to find the different stencils of the PDE can be implemented easily. The shapes where you scatter off the implement through splines. So they can calculate the matrix on the fly. They've done it. They have checked what are the resource requirement, and it can beat a current generation supercomputer for problems that need more than 1 million years. No, sorry, 1,000 years. So this is again something where we need to see, can we speed this up like Matt showed for the quantum chemistry, but this is going to be hard. And so maybe one should look at the problem of what do we do with the quantum machine, not by looking at something that we can do, quantum mechanically, and then hoping that it's hard classically, but let us just look at what are the main applications that run on the petascale machines. And I have by now a slightly outdated slide from my colleague Thomas Schultes. He made a list of the top performing codes that worked that ran on the Jaguar machine in Oak Ridge, which was the first machine to break through the petaflop barrier. And all of the codes that reached more than a petaflop are material simulation and chemistry problems. So this is the big challenge. This is what supercomputers are used for, and that really stresses them out. This is what brings up the power consumption. The climate models need much less power because they're memory bound and not compute bound. So this might be the killer app, and we heard from Krista and from Dave already what one would do with it. We'd look for room temperature superconductors, carbon sequestration, nitrogen fixation and more. There would be many things to do if we had such a machine. And let me skip over this because I think Matt probably showed how one does it on a quantum machine. And we now know how to do or how we could potentially do a quantum simulation of a molecule with about 100 electrons or so if we had a quantum computer. But now we want to tackle that question not of the catalyst, the molecule, but we want to find this room temperature superconductor. And the challenge there is I need to now model this slab of the cuprate. It's not just a simple molecule, it's a big crystal. I need to look at least at maybe 10 times 10 unit cells. I have at least 10,000 electrons. It's about a factor of 100 bigger than those molecules. The scaling is still at least 10 to the 5. The runtime is a factor of 10 to the 10 longer. And we're back at millennia and more. Although we have now much faster algorithms. So what do we do there? We do the same as what we've done with the analog quantum simulators. We go back to effective models. I suppose we should not just solve the material brute force, but let us simplify it classically first. Let us go down again to the Hubbard model. And then the question is, this Hubbard model, which was still hard classically, can we solve it efficiently on a quantum computer? And that one can. That has been proposed since nearly 20 years. Abrams and Lloyd proposed that one can use the quantum computer to simulate the time of the evolution under the Hubbard, but the Hamiltonian. That's great, but they didn't show more. They didn't show how to do it, how hard it would be. There was more in a paper by Ortiz et al. They showed how one maps the fermions to qubits, but they did not show the circuits. They did not calculate the gates one needs. They did not look at the runtime. And when showing how to measure things, they were cheating. Because in their plots, they showed the expectation values under the wave function and made beautiful plots of what one would get and that it's what it should be. But if you have a quantum computer, you can't just read out the wave function, but you can only sample, and then you get a single bit per measurement and not a nice average. And so you have to sample. And it's much, much harder than you think. So those are things that we work on now. The advantage of the Hubbard model is that the Coulomb term drops down from n to the 4 terms to just a single term. The Hoppings terms and the Coulomb terms you can all apply in parallel. The Hubbard use just locally, so it's easy. Those you simply apply in parallel. The Hopping terms, there's the trick by Bravia and Kitaev how one can also do them in a constant time. So you can do a time step using the Hubbard model in constant time independent of the problem size. I still have to prepare it. That takes time n squared. Since we think that the gaps might close like 1 over n. But it's still a beautifully nice scaling. And so the Hubbard model will be much easier than doing molecules. One still has to find out how do we prepare the ground state? How does one find the ground state? how long does that take? How do we measure correlation functions? If we look at superconductivity, we have pair correlation functions. There are n to the 4 terms here. The scaling goes up again, and we need to see how to do it nicely. So let's assume we're there now, and we built a beautiful quantum computer with 2,000 qubits. We solved the Hubbard model in half a second. What have we gained? And I asked the question to one of my material science colleagues who does simulations, if she'd be excited if I gave her a machine to solve the Hubbard model. And she said no, she would be totally unexcited. She would be totally bored and would not even look at it. Why? Because the Hubbard model doesn't describe anything in nature. Well, except ultra-cold atoms in optical lattices. So it might be useful to teach us fundamental mechanisms about the physics of such systems, but it will not give us quantitative predictive power. Now, I got my colleague interested in the Hubbard model by telling her, if the Hubbard model doesn't describe a material and you like designing materials, why don't you design a Hubbard material? Why don't you look for a material that is well described by the Hubbard model? She liked the challenge. She found one now that might be. And her challenge now, she does a solid state quantum simulators for ultra-cold quantum gases. But what she would really like to have is quantitatively predictive power. She would really like to say, okay, if I build this material, if I mix it in crystal, it has these properties. TC is 200 Kelvin now or something. And we cannot yet do a full initial simulation because using 10,000 spin orbitals or more is just too hard. We will never do that unless somebody gives us a really, really fast femtosecond gate time quantum computer. So the solution that I see is that we go hybrid. That we use classical algorithms to find effective models that are more quantitative than the Hubbard model, that can quantitatively describe the material, and then use the quantum machine to solve those effective models and then get quantitative answers out and try to iterate that. And those methods we are now also working on. So, so if we view quantum computing not just as a nice mathematical game, but as a post-exascale technology, then it's hard to find those killer apps, because the problem has to be too hard for a future exascale machine. We have to have a quantum algorithm to actually solve it faster. The crossover scale has to be shorter than our lifetime, and it's just extremely hard to compete against Burton or Dark when they build special purpose classical hardware. But that's our competitor. Factoring and code breaking is of limited use. Quantum chemistry, I think, is one of the clear applications. Solving linear systems, well, I don't know yet which ones we can't solve well enough yet. There might be others. Machine learning is one hope, but we don't know yet how to do it. But I think having one killer app is already great. And what I want to basically say here is summary, it's time that we view quantum algorithms and quantum algorithm research not just as a theoretical computer science field, but in the context of classical HPC, which are the really hard application problems that people want to solve, but people invest billions, and can we really compete there? And that's the challenge we need to address. Thank you.
If The Fermi-Hubbard model
Yeah.
is insufficient for designing some of these materials. What would the proper model be, and what's the actual complexity of simulating it?
The proper model would have to include at least all the bands of the cuprates, and that maybe it's enough to take the 5 d orbitals. We have then 3 p locally. We have 1 s, so that's about 9 orbitals locally. Then we have the oxygens. We need at least 2 of the p bands there. So we need at least about a 20-band model per unit cell. Maybe one can bring that down to a 10-band model, a 5-band model, I don't know. But then that's just a single unit cell, and then you need to go there to a bigger system. You can do that exactly. That might be challenging. Or you can once more mix that with some hybrid approaches, mean field-like, and find something that's better. So it will be hybrid in the end, I think. But it's well beyond a 1-band model. It's at least a 3-band model, probably more a 5 or a 10-band model.
If one built a quantum memory to hold the cell, each cell, you just move the circuitry on top of bring the cell out of the quantum memory, do a time step, put it away, bring another one out, do a time step, put it away.
That's doable if we have short-range interactions. The Coulomb interaction is screened, but not at the length scale of 1 unit cell. And there's also one problem with the Hubbard model. It just has the local part of the Coulomb energy. We think that's not enough to explain the physics quantitatively. But you might be able to truncate it after 3, and then the scaling is not too bad for the effective model. If you want to do the full one, then you need to also have the screening of the Coulomb interaction emerge from the simulation. It's much better to estimate the screened one classically and then solve the effective model with the screened interaction.
So this is a very thought-provoking talk to end the session on. And, but have you looked at or talked to, say, biologists, that does biology give some potential applications where quantum computers would be good? And certainly one area where I can think you need an enormous amount of computation is verifying software.
Yes. So let's first talk about biology. At the same session on the post-exascale computing, one talk was by people from the Shor on their Anton 2 machine for protein folding. And that's really nice special purpose hardware that shows what one might be able to do. But they said they would love to have a quantum computer if we could build one, because, no, not because they can't fold the protein, they can easily. The problem is that you need to know the forces accurately enough, and the classical force fields they do are just not good enough. So I wouldn't calculate the force on that big protein quantum mechanically, because then things get far too slow. But we need to look at bits and pieces, cis polarizations of bonds and so on, and get better classical force fields on from the quantum hardware and use them then in this hybrid approach.
This is interesting because the forces get inaccurate in Anton when they're very short range.
Yeah.
And so one could imagine doing the molecular dynamics that Anton does, generating a configuration of the atoms.
Yeah.
You know where the coordinates of all the nuclei are and all that stuff. You know where the orbitals are likely to be and so on. Formulate that as a quantum computer problem, compute ground state energy, and go in that direction, and then go back and forth. Now we've seen MD and quantum chemistry used together, but not quite that way.
Yeah.
And that might be a way of.
For the time scales that Anton wants to go to, these millisecond scales, you need to be able to calculate the forces in microseconds. So you need to do those things not in hours, but in microseconds. that's challenging. I don't think we'll do that. I think when we look at the typical linear configuration, do them offline, parameterize it, find out what happens, and then improve it. Find out it doesn't do what nature does, so one checks again what would one have to improve. But yes, they would be a customer for such a machine to help them get the force fields better.
Might be able to afford it too.
Oh yeah, sure. Well, it depends on what you sell it for in the end. Maybe cloud service. But then there was the question also,
That was my point.
Yeah.
Yeah.
bio then, the rest is mostly clustering of data, machine learning problems. I don't know. Yeah. Then you get the second question, second area?
There's a lot of work, particularly in Europe, on verifying software,
Yes.
proving software correct. And there are these
That's why Lockheed Martin bought a D-Wave machine. It's just, yes, we want to look for quantum algorithms to solve hard optimization problems, case problems. We don't know if quantum hardware helps there or not.
So I think your talk is a testimonial to the importance of computational thinking. You want to find the abstractions and models for the problem at hand that are amenable to the kind of computational device that you have.
Yeah.
One final question.
Okay, so let's suppose some theoretical computer scientist is going to take your device at the bottom. So here's the natural question. So what are new problems to look for? So we know phase estimation is kind of a very quantum problem. It's wonderful. I think Matt has talked about some application of it. But then what are the other quantum algorithm problems that are solving quantum problems, or where to look for? My colleagues are looking at graph isomorphism.
Okay, so the first advice I have to theoretical computer scientists is to talk to application people. I found a huge gap there often, even classically. So then the other big question is quantum mechanics is intrinsically linear. How easy is it to solve nonlinear problems? Linear ones, but nonlinear problems might be hard. But you need to know a range of application problems to then be able to match your quantum algorithms to maybe something that somebody wants to solve. So my advice is talk to application people, talk to people in supercomputing and what they do.
I'd like to make a quibble about the linearity. Certainly, unitary operations are linear, for sure. But when you start mixing classical control with quantum operations, then you can be...
Don't give away all our ideas.
Let's thank Matthias again for a great